Alright, next comes how do we actually do addition. Well, let's talk about how we would do addition normally. So if you have 9.999 times 10 to the first plus 1.61 times 10 to the negative 1, we want to be able to add the two. Well, first off, if you notice that these numbers are not going to, you can't just simply add these two numbers yet, because this one does not have the same power that it's raised to as the first one. So in order to do that, we need to what they call align the decimal points. So we need to convert this number to the larger number, and you always convert it to the larger. So to make this go up, we got to raise it by 2, which means we need to downshift this number twice. So that's why it becomes 0.016. Hey, notice if we were doing 4-digit decimal addition here, we just lost a digit here. That's very important to recognize, because that also happens in binary land, and you will lose some precision or some information whenever you're doing any type of addition, multiplication, so forth and so on. So then you go ahead and you add the significands, aka the fraction slash mantissa. And so because now that the exponents are aligned, you can just add these two numbers, you get this. And then you normalize the result and then check for under and overflow. Well, you can't just say 10 is not normalized, so we need to go ahead and shift it down by 1, which increases the exponent by 1. And then we have to round and renormalize if necessary. Notice, oh, by the way, I'm sorry, the check for over and underflow is if it goes past, let's say that it became 10 to the 400, which cannot be represented by floating point or double floating point, so you'd have to call it overflow and then call it infinity. That's what it means by overflow. Underflow is if it became like negative 400, then you underflowed the number. But this is obviously not under overflowed, because 2 is definitely within the range of both floating point and double. And then after that, you do need to round, because in this situation we're only doing 4 digits of precision. So, and this has 5 digits, so we go ahead and round it to 1.002. Notice again, we have lost some precision because we had to round. So this is a good example of showing how certain digits just fell off in this floating point representation. So keep that in mind. That floating point is not going to be, I should say, absolutely precise. It loses bits here and there all over the place. Alright, now consider, let's do another example. Ooh, we get to do a negative example. So 2 to the negative first and 2 to the 2. Notice that we always go, well, you can see here's a decimal. First we need to normalize it to the largest number. The negative 1 is larger than negative 2, just in case anyone didn't see that. So we shift all the numbers over. So here we go, we shift them so the exponents are the same. We add the significands. Notice that you're actually subtracting here. So then it was 0.002 times 2 to the negative first. Now you have to normalize it, well, because that's the 1 needs to be over here. So we need to, 1, 2, 3. So we want to shift that decimal point down 3 times. We need to subtract 3. There's no over or underflow, that's great. And there's no change or need to round and renormalize, so then we're done with our answer. Alright, great. So how do we actually do this in hardware? By the way, we're not going to do this in Verilog. It's much more complex than integer add, although it ends up being a lot of integer adds and some control in the end of the day. Doing it in one clock cycle takes too long. So most floating point units take multiple clock cycles in order to even do a simple add. Alright, so that's why the adder usually takes several cycles to complete, and it can be pipelined, namely you start one add and then you begin the next add afterwards. And hopefully this architectural diagram will make at least some sense to you. Alright, so I know this is going to be very confusing, but the best way to understand this is let's first look at what we have up top and then what are the steps. So we have our two numbers, sine, exponent, and fraction, sine, exponent, fraction. These are both a floating point and double. The two steps are first you compare the exponents and then shift as necessary, aka you're going to align the two numbers so you can straight up add them. Then you go ahead and you do the add of the significants. Then you're going to normalize it, meaning that you're going to take it and you're going to try to shift that decimal point so the 1 is directly to the left of it and there's just a 1. And then you're going to go into what they have, a rounding hardware. Now, I know this maybe, we didn't go through an example here, but it is possible that after you round it, you now need to renormalize it, because if you round it and that bit flies all the way up to the top, you're going to have to shift it again. So this normalize and rounding may happen more than once. And then when you're done, it becomes the final answer. All right, let's go ahead and take a look at what's going on here. Notice that the exponents first go to this small ALU, and that is where they determine the exponent difference, and that'll help the control logic determine which exponent is larger. And once it knows which exponent is larger, it then knows that there's 3 muxes here. One mux, the first mux is going to forward the exponent of one of them all the way down here, and this mux is going to forward which way it needs to shift to the right. And this is where the, let's see, the ALU should also come in with the fractions right here. So it has the fraction. Notice one of the fractions is going to be shifted, the other fraction is not. So this control is going to let one of these two numbers be shifted and the other one not be shifted. And then this one is going to forward the bigger exponent down here. Alright, so this control figures out from the difference of the small ALU which one needs to be shifted, and of course by how much. And then this, so that's what the first step is. The next step is doing the big add, because that's going to take pretty much one whole step or one whole cycle. And that's from the shifted number and the other shifted number, and then it forwards it along. Notice that you still have a couple of muxes down here, because the issue is that, well, this has to do with the looping structure. So let's just assume for the moment that the big ALU comes down here, and then the answer of this should come back to the control, which it does, great. And so the control, after coming from the ALU, will notice if it tell it if it needs to shift left or right and by how much. And then also notice that down here, it was receiving the largest exponent, and since it has a result of the ALU, it can determine how much it needs to increment or decrement. Again, ignore these two muxes for now. And so once it's normalized, because it has the largest exponent and it's incremented or decremented depending on how much and by how big came out the ALU as well as the shift, then you go into a rounding hardware that goes and sees how many extra bits, because when the big ALU completes, it's going to have a wider number of bits, well, one extra bit in the front, and then when you do shifting, it's going to have extra bits to the right in order to capture or help with the rounding. And then the rounding hardware is going to look at those extra bits and determine if it needs to round. Notice that the rounding does go back, let's see, there should be a bit that goes back, yeah, here it is. So right here, rounding hardware does go back to the control. And so at this point, if rounding, additional round of normalization is needed, that's where these numbers come back to these two muxes. So the control will say, hold on, we still need to re-normalize this number, and then it gets normalized again and then back into the exponent. All right, pretty confusing, I understand. Couple of takeaways. The big takeaways here is adding a floating point is not a single step process like it was with integers. There is a lot of control and different things running around in order to support this. And it can be somewhat confusing. Again, we're not going to go too much into floating point, but it is important to at least recognize its complexities. So the FT multiplier is similar complexity of the adder, but using a multiplier for significans instead of an adder. So luckily for multiplication, you really just end up swapping out this big ALU. And the other thing is you need to have extra hardware for being able to shift more than you would with an adder, because when you multiply, things can shift a lot more. So FP hardware usually does addition, subtraction, multiplication, division, reciprocal, and square root. Yeah, that's right. There is square root inside of hardware. And it also does the FP to integer conversion for you. And all these operations usually take multiple cycles, but they can be pipelined. What does that mean by pipelined? Well, you may do your first FP right here, which does a normalization, and then when it's in its adding stage, you can put the next instruction here so that it at least can be normalized while the adding is complete. Then that adder can go down here, while what was just normalized can be to be add, and then you can get in a third one. And this is called pipelining, which is highly advantageous, and we'll talk more about that next class. Alright, inside of MIPS, and we talked about this actually with x86. Hopefully the x86 implementation makes a little more sense. But the MIPS version is the same, where you have special floating point registers, and then you need to pair them if you wish to support double. And we did go through this in class, so I actually do not need to go over this again because we covered it in your assembly. That's where you were tested over it. Wow, we get to skip all this. That's great. All right, lastly, accuracy in the arithmetic. The standard does specify additionally rounding controls, what's called the guard, round, and sticky. This is just how you want to do rounding. I'm not going to go into this too much right now, but the basic idea is that if you wish to do standard rounding, truncating, or always round, you can actually set that in hardware. Normally just rounding is selected. The one thing to keep in mind is not all floating point units implement all options, but most programming languages just use the default, which is round, I believe. And so this has been kind of a de facto standard of just sticking with rounding. You will need to read a little more into this in your book for one of the problems, because the idea of there's the guard, which is just an extra bit, there's the rounding bit, which always tells that it's rounding, and there's a sticky bit, which just is used to signify, hey look, we've lost a lot of bits going to the right. Another type of parallelism that is good to talk about, although you won't have this for your book, is that you may be able to do multiple adds inside of one long adder. So for example, if you have a 128-bit adder, that means you can do 16 8-bit adds, 8 16-bit adds, or 4 32-bit adds. How is that possible? Well, for example, 128-bit number is really just 4 32-bit fields, or 8 16-bit fields, or 16 8-bit fields. And so you could have a piece of hardware that just operates on those individual fields. In x86, there was originally called the 8087 coprocessor, back in the early 80s, and it did use a push-down stack, which we're not able to talk about because I can't guarantee that everyone here is taking discrete math, so we'll skip that for now. But the thing here is that the 8087 had a separate processor simply for doing floating point because of how complicated this was. Nowadays, all floating point is built into the processor because we have enough area due to Moore's law to put in as much hardware as we want. Unfortunately, it was very difficult to generate optimized code. Alright, and we went through this already. We're not going to do streaming or matrix multiply. Actually, matrix multiply we're going to do right. Alright, let me pause for a moment.